ఒక 30 to 40 minutes అవుతుంది సార్ అంతే.
నేను 30 minutes
అదే
స్టార్ట్ చేస్తాను.
ఇది స్టార్ట్ అయిపోయినది
పీపీటీ చేస్తాను.
స్టార్ట్ అయిపోయినట్టు కదా.
ఓకే సార్.
ఓకే సార్. Dear students, welcome to GDC Men's Srigakulam YouTube channel. Today I am going to explain preparation of aldehydes and ketones. We know that carbonyl compounds, the functional group of carbonyl compounds is C double bond O. If the C double bond O is attached with at least one hydrogen, it is called as aldehyde. So this is the general form of aldehyde, R C double bond O H. The simple aldehyde is attached with two hydrogens, that is called as formaldehyde. This one is formaldehyde. Suppose if the C double bond O is attached with two alkyl groups, then it is called as ketone. RC double bond OR, it is named as ketone. In this video we are going to learn preparation of aldehydes and ketones. The first method is we can prepare both aldehydes and ketones from acid chlorides, RC double bond O Cl. Okay, this is the general formula of acid chloride. We can prepare aldehydes from acid chlorides by using Rosenmann's reduction. This is the best method for the preparation of aldehydes from acid chlorides. In Rosenmann's reduction, the reagent is hydrogen and palladium is the catalyst deposited over barium sulfate, and this catalyst is poisoned by phenolene and also very trace amount of sulfur. This composition is called as Rosenmann reagent. When you treat RC double bond OCl with the hydrogen molecule in presence of Rosenmann's catalyst, that is palladium deposited over barium sulfate and poisoned by phenolene and a trace amount of sulfur. Simply there is a replacement of chlorine by hydrogen and there is a formation of respected aldehyde and also hydrogen chloride. So this is the very simple and best method for the preparation of aldehydes from acid chlorides. Let's take a simple acyl chloride. Let us take CH3COCl. When you treat with a hydrogen molecule in presence of a Rosenman catalyst, there is a formation of acetaldehyde, CH3 C double bond OH. Formaldehyde cannot be prepared by using Rosenman's reduction reaction. We can prepare other higher aldehydes by using Rosenman's reduction. And also we can prepare ketones from acid chloride. When you treat acid chloride with the dialkyl cadmium, then simply there is an insertion of R group, there is a substitution of R group in place of chlorine, and there is a formation of ketone and also CdCl2. Suppose if you take 2 moles of RCOCl, there is a formation of 2 moles of ketones and there is a formation of cadmium chloride. Okay, by changing alkyl group we can prepare different ketones. Okay, let's take CH3COCl. This one is acyl chloride, and when you treat with C2H5 twice dimethyl cadmium, here in place of chlorine there is a substitution of ethyl group. So there is a formation of CH3 C double bond O C2H5, that is CH2CH3 and cadmium chloride. So if you treat with 2 moles of acyl chloride with 1 mole of diethyl cadmium, there is a formation of 2 moles of ketone. The ketone is 2-butanone or butanone. This is the ketone you will get. You can prepare aldehydes and ketones. In this way you can prepare both aldehydes and ketones by using acyl chloride. You can prepare aldehydes by treating with hydrogen in presence of Rosenman catalyst, and also we can prepare ketones when you treat with dialkyl cadmium. And the second method is from 1,3-dithiones. These are cyclic acetal, thioacetals. Okay, this is the structure of 1,3-dithiones. And 1,3-dithiones has 2 acidic protons. These are slightly acidic protons when compared with other protons. So this one is called as 1,3-dithione. It's a cyclic thioacetal. So when you treat When you treat 1,3-dithione with a strong base such as N-butyl lithium, so this is 1,3-dithione, hydrogen and hydrogen. When you treat with a strong base, that is N-butyl lithium. Okay, here butyl has partial negative charge, lithium has partial positive charge. In N-butyl lithium, the butyl group acts as a base and abstracts proton. So there is a formation of carbanion. This carbanion is stabilized due to electron withdrawing nature of sulfur. And here there is a hydrogen and there is a formation of carbanion. This carbanion acts as a nucleophile. First there is a formation of carbanion, this one acts as a nucleophile. This nucleophile participates in the nucleophilic substitution reaction. When you treat with alkyl halide, okay, when you treat alkyl halide with nucleophile, there is a nucleophilic substitution reaction. So there is a substitution of halogen by this nucleophile. So there is a formation of monosubstituted 1,3-dithiazide. So here one of the acidic protons will be replaced by the alkyl group. This one is monosubstituted, alkyl substituted 1,3-dithiazide. If you hydrolyze monosubstituted alkyl substituted in presence of acidic mercuric chloride, upon acidic hydrolysis in presence of mercuric chloride, there is a hydrolysis reaction takes place, and here there is a formation of dithiol SH and SH. This one is 1,3-dithiol. 1, 2, 3. This one is 1,3-dithiol, and also there is a formation of aldehyde, R C double bond OH. So if you take monoalkyl substituted 1,3-dithiazide upon acidic hydrolysis in presence of mercuric chloride, there is a formation of aldehyde. So this is the preparation of aldehyde from 1,3-dithiazide. Let's take the same 1,3-dithiazide. Let's take an example. 1,3-dithiazide. These two are slightly acidic hydrogens. When you treat with the N-butyl lithium, the N-butyl lithium, it's a strong base. The butyl group abstracts proton. This one abstracts proton, and here there is a formation of carbanion, sulfur, and this one hydrogen. Here there is a formation of carbanion. Okay, when you treat with let's take an alkyl halide CH3Br. Let's take an alkyl halide. This nucleophile attacks on the methyl group. There is a nucleophilic substitution reaction, SN2 type of nucleophilic substitution reaction takes place, and here there is a formation of monosubstituted or methyl substituted 1,3-dithiazide. Okay, when you hydrolyze this 1,3-dithiazide compound in presence of acid and mercury chloride, acidic hydrolysis in presence of mercury chloride, there is a formation of CH3 C double bond O H plus 1,3-dithiol SH. Simply here there is a breaking of these two bonds. Here there is addition of hydrogen, here there is a addition of hydrogen, here there is a oxygen, here there is a addition of oxygen. So here there is a formation of CH3 C double bond O H, and here SH CH2 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 SH. So you can prepare acetaldehyde by using 1,3-dithiazide by reacting with N-butyl lithium, and after that it is reacted with methyl bromide, and after that acidic hydrolysis in presence of mercury chloride, there is a formation of acetaldehyde. This one is acetaldehyde. Let's take ketones. You can prepare ketones also. Let's take the same 1,3-dithiazide. This one 1,3-dithiazide. So these are two acidic protons, slightly acidic protons when compared with the remaining protons. And here when you treat with the very strong base N-butyl lithium, it has negative charge and this one has positive charge. This one acts as a strong base and there is an abstraction of proton, there is a formation of carbanion. There is a generation of carbanion. This one acts as a nucleophile. When you treat with alkyl bromide or alkyl chloride, alkyl halide, let's take alkyl bromide, there is a formation of alkyl substituted monoalkyl substituted 1,3-dithioates. This one is sulfur and hydrogen, and here there is a nucleophilic substitution reaction. This nucleophile attacks on the alkyl group and there is a leaving of bromine. There is a SN2 type of nucleophilic substitution reaction, and there is a formation of monoalkyl substituted 1,3-dithiane. Again, this one is monoalkyl substituted. Again, when you treat with this monoalkyl with the strong base, here you have another acidic proton. This acidic proton will be abstracted by the base. So this one will be abstracted by the base. Here there is a formation of carbanion. This is the R group and sulfur. Here there is a formation of carbanion. This carbanion again acts as a nucleophile. This one acts as a nucleophile. When you treat with alkyl bromide, here there is a nucleophilic substitution reaction. So there is a formation of, let us take R dash, let's take different alkyl bromide. Then here there is a formation of dialkyl substituted 1,3-dithiane. This one is R dash and this one is R. Again, you have to perform acidic hydrolysis in presence of mercury chloride. So in acidic hydrolysis, simply here there is a hydrolysis takes place. Simply here there is a hydrogen, attachment of hydrogen. Here there is a attachment of oxygen to the carbon. So here you will get R dash C double bond O R plus 1,3-dithione. This is the 1,3-dithione. Here there is a formation of ketone. Suppose if you take monoalkyl, when you perform acidic hydrolysis in presence of mercury chloride, there is a formation of aldehyde. Suppose if you take this one, when you perform acidic hydrolysis in presence of mercury chloride, there is a formation of aldehyde, RC double bond OH. At this stage you will get aldehyde. But if you convert monoalkyl substituted 1,3-dithiane into dialkyl substituted 1,3-dithiane upon acidic hydrolysis in presence of mercury chloride, there is a formation of ketone. This is the difference. Let's take an example. Okay, let's take 1,3-dithiane. So this is the 1,3-dithiane. When you treat with N-butyl lithium, there is a abstraction of proton. There is a formation of carbanion. There is a formation of carbanion. Let's take an alkyl halide. Let's take CH3Br, methyl bromide. So here there is a nucleophilic substitution reaction, and there is a formation of methyl substituted 1,3-dithiane, hydrogen, and here there is a methyl group. Okay, let's react this mono substituted with again N-butyl lithium. Here there is a formation of carbanion, sulfur, and here this proton will be abstracted. So here there is a formation of negative charge. Here here there is a formation of carbanion, and this one is methyl group. Okay, when you treat with, let's take another bromide, alkyl bromide, that is ethyl bromide. Here there is a nucleophilic substitution reaction. So there is a formation of ethyl methyl substituted 1,3-dithiate. Here you have ethyl group, and here you have methyl group. Okay, upon acidic hydrolysis, in presence of mercury chloride, HCCl2, H2O, there is a formation of ketone C2H5, C double bond O, CH3 plus 1,3-dithiol, SH, and this one is SH. Okay, this is about the preparation of aldehydes and ketones by using 1,3-dithioates. And from nitriles, we know the general formula of nitriles are C triple bond N, and hydrogen cyanide, this one is inorganic molecule HCl. From nitriles we can prepare aldehydes and ketones. If you take hydrogen cyanide, suppose if you take hydrogen cyanide, so when you treat with alkyl magnesium halide, that is Grignard reagent, this one is Grignard reagent. If you take equal amounts, equivalents of same equivalents of hydrogen cyanide and alkyl magnesium halide, there is a nucleophilic addition. This one is nucleophile. This one has positive charge. This nucleophile attacks on the carbon here, and these lone pair of electrons attacks on the MgX. So here there is a formation of hydrogen H. See, here there is attachment of alkyl group and double bond, and this one has a negative charge, and here there is a Mg plus X minus. On acidic hydrolysis, when you perform hydrolysis in presence of acid, okay, there is a addition of oxygen and wait, class. So upon acidic hydrolysis, there is a formation of, here there is insertion of oxygen, and there is a formation of aldehyde, RC double bond OH. So in this case there is a formation of aldehydes. But in this method you have to take equal moles of hydrogen cyanide and alkyl magnesium halide. Suppose if you take alkyl cyanide, RC triple bond N, when you react with the alkyl magnesium halide, RMgX, okay, here this one has negative charge, this one has positive charge, this one attacks on the carbon, so RC double bond, and here we have R dash and negative charge, this one is MgX. Suppose if you perform acidic hydrolysis, H3O plus, simply here there is a insertion of oxygen, here 2 hydrogens, here also there is a acidic hydrolysis, here insertion of 1 hydrogen, here there is insertion of OH. So finally here 2 equivalents of H2O molecules are participated. Okay. In this one H2O, if you take one H2O, oxygen will be attached with carbon and 2 hydrogens will be attached with nitrogen. If you take another H2O molecule, one of the hydrogens will be attached with nitrogen and OH will be attached with MgX. So finally you will get RC double bond O, R dash plus NH3 plus MgX OH. So you can prepare alkyl. If you take alkyl cyanide, This one is alkyl cyanide or nitriles. If you take, when you treat with one equivalent of alkyl magnesium halide, upon acidic hydrolysis, there is a formation of ketone. But if you take excess amount of alkyl magnesium halide, then there is a further reaction, then there is a formation of respective tertiary alcohols. So if you want to prepare ketones, you have to take one equivalent of alkyl magnesium halide from carboxylic acids. Okay, from carboxylic acids we can prepare aldehydes and ketones. If you take barium, calcium, barium or strontium, salts of carboxylic acids, you can prepare aldehydes or ketones by pyrolysis or distillation of carboxylates of calcium, barium or strontium. Let's take carboxylates of calcium. Let's take suppose if you take H, a simple carboxylate, HC double bond O minus, and here HC double bond O minus, and here Ca2 plus. Okay, we are taking the calcium formulate. When you pyrolysis, when you heat this compound, there is a removal of calcium carbonate. Here there is a removal of calcium carbonate, CaCO3, and here there is a formation of formaldehyde, very simple aldehyde, CaCO3. This one is a pyrolysis reaction. When you heat the salts, calcium salts of carboxylates or barium salts of carboxylates or strontium salts of carboxylates, there is a formation of aldehyde. Suppose if you take two different salts, let's take H C double bond O minus, H C double bond O minus, and Ca2 plus. This one is one salt, and let's take another salt, RCO O minus and RCO O minus. I am taking a mixture of two calcium carboxylates. Let's take, when you heat these two carboxylates, in this case you will get aldehyde. In this case you will get 2 moles of aldehydes, RC double bond O H, and there is a 2 moles of calcium carbonate. In this case this HC double bond O will be attached with R2, so there is a formation of RCO H. This SCO will be attached with alkyl group, or you can say RC double bond O is attached with hydrogen, RC double bond O H is attached with hydrogen. So if you take two different things, you will get if you take calcium salts of formulates, and if you take any carboxylate, calcium salts of carboxylates, then you will get aldehyde. If you take only formulates, calcium salts of formulates, you will get formaldehyde. If you take calcium salts of formulates and calcium salts of any carboxylate, then there is a formation of aldehyde. Okay, let's take any carboxylate, RC double bond O minus, RC double bond O minus. Okay, let's heat this compound. In this case, simply there is a removal of calcium carbonate, and there is a formation of RC double bond R. There is a formation of symmetric ketone. Suppose if you take two different carboxylates, C double bond O minus and RC double bond O minus and Ca2 plus. Let's take another thing, another carboxylate, RC double bond O minus and R dash C double bond O minus, and you are taking mixture of two calcium carboxylates, different carboxylates. Okay. Upon pyrolysis, there is a formation of RC double bond O R dash. RC double bond O R dash. 2 moles of RC double bond O R dash. 2 moles of calcium carbonate. Okay. This is about the preparation of aldehydes and ketones from acid chlorides, from 1,3-dithiones, and also by using nitrites, and also by using salts of from carboxylic acids, that is calcium, strontium, barium salts of carboxylic acids. Thank you very much.